Namaskar and very good afternoon, esteemed guests, speakers, participants, ladies and gentlemen. My name is Shikha, and on behalf of SIGRE India and CPIP, it's my honor to welcome all of you to this international tutorial on methods for dielectric characterization of polymeric insulation materials for outdoor application under the aegis of SIGRE National Study Committee D1 on materials and emerging test techniques. For opening session, we have with us Mr. A.K. Bhatnagar, Director SIGRE India and CPIP. We are honored to have with us Shri B.P. Muniji, National Representative in SIGRE Study Committee D1 and GmBHEL, and Dr. Jens SIFERT from Germany, and who is the faculty for today's tutorial. As you know that today's tutorial will be taken by Dr. Jens. This will be 90-minute session including question and answer session at the end. We have requested Dr. Jens to kindly take question at the end of his presentation. Participants may also send their queries to SIGRE India for forwarding the same to Dr. Jens for a response after the tutorial. Ladies and gentlemen, SIGRE, as you know, is a unique platform to share practical experiences. Before I invite Mr. A.K. Bhatnagarji, Director SIGRE India and CPIP for welcome address, we would like to display a film about SIGRE for the benefits of the participants who are not much familiar with the activities of SIGRE. So I request our IT team to kindly display the SIGRE film.
SIFERT, the International Council on Large Electrical Systems, is World Forum for Power System founded on November 22, 1921 at Paris. SIGRE deals with the issues related to the development, operation and management of electric power systems as well as design, construction, maintenance of equipments and plants. Mission of SIGRE experts from all around by sharing knowledge and joining forces to improve the electric power systems of today and tomorrow. It mainly aims on coordination of research, exchange of experience, scientific and technical information on the operation and design of electric power systems. SIGRE is an association that promotes the exchange of latest generation of technical knowledge and bringing innovative ideas to support the industry needs. SIGRE has worldwide network of experts from ministries, generating companies, transmission and system operations, distribution operators, regulators, manufacturers and academies. It has gained international representation in nearly 90 countries through national committees in order to provide opportunities for improvement of services supplied to the society. SIGRE has 16 national committees, 95 member countries, more than 10,000 individuals and more than 1,000 organizational members. SIGRE strategic direction are best use of existing system, unbiased information for all stakeholders, environment and sustainability, and future power systems. The challenges are renewable energy sources, growing environmental requirements, limitations to build new transmission infrastructures, architecture of networks, operation of existing power systems, transmission of large amount of power over long distances, cybersecurity, and intermittency of renewable power generation. SIGRE operates through 16 committees on different subjects having members from various countries. These committees are divided into 4 groups. Group A, Equipment, and the study committees are A1, Rotating electrical machines, A2, Transformers, A3, high voltage equipment. Group B, technologies, and the study committees are B1, insulated cables, overhead lines, substations, HVDC and power electronics. B5, protection and automation. Group C, systems, and the study committees are C1, system development and economics, system operation and controls, system environmental performance, system technical performance, electricity markets and regulation, distributed system and dispersed generation. Group D, new materials and IT, and the study committees are materials and emerging test techniques, information systems and telecommunication. The study committee of SIGRE has about 250 working groups which produce nearly 50 technical brochures per year. The work carried out in SIGRE environment is considered as reference being applied to the development of technical standards. SIGRE develops technical knowledge using two main methods: conferencing and meetings, where papers are presented and discussed, and studies carried out by study committees through the work of international working groups on identified industry issues. SIGRE has recently started a series of science and engineering journal. 6 issues have been published in 2015-16. SIGRE has started series of new publications named Green Books. The books on the following subjects are already released: accessories for HV extruded cables, overhead lines, and utility communication network and services. So, why is it especially profitable to join SIGRE activities? Joining a SIGRE working group as an expert always result in a high return for your organization as well as for yourself, all the more so for a young engineer. You become part of a worldwide network of experts with whom you discuss current issues, share international experience, and benchmark your own practices. You are in a position to promote your ideas and weigh on the contents of specifications, recommendations, and future standards. Experts represent all the profiles of the power industry, hence a wealth of opportunities to start cooperation between university and industry, between industry and administration, etc. At a personal level, you are in contact with other cultures, practices, working methods. You acquire knowledge through working and experienced experts. National international teamwork and practice of technical English enhance your personal development. New generation networks. National Committee of Countries, US, Australia, New Zealand, etc. have created a next generation network, NGN, that aims to develop the next generation of power engineering professionals. SIGRE is present in India since 1971. Since its foundation, SIGRE India helps the country to deal with its challenges in the areas of electricity and demonstrates the strength of the Indian power system engineering worldwide. The SIGRE India brings together top experts spread across 16 minor study committees at national level. The dissemination of consolidated knowledge is done through publications and national and international workshops, seminars, symposia, etc. So, get associated with this unique organization and take maximum advantage of this forum for accentuating the knowledge in electric power system.
Thank you. I We are also honored to have Dr. Constantine, who is the former chairman for SIGRE Study Committee B2 on overhead lines, with us. So now, without any further delay, I request Shri A.K. Bhatnagarji, Director SIGRE India and CPIP, to deliver welcome address. Sir, please.
Thank you, Shikha. Good afternoon, friends and my colleagues, participants. I welcome you all on this online tutorial on methods for dielectric characterization of polymeric insulation material for outdoor application, being organized by SIGRE India under the aegis of SIGRE National Study Committee NSC D1. Ladies and gentlemen, you are aware this unusual situation of COVID-19 has badly affected the activities and dissemination of knowledge. But nevertheless, this is an opportunity to learn, and this is how we are into online learning in this situation when options of physical conferencing are limited. SIGRE India, with the guidance and support of SIGRE Study Committee, has planned a series of international tutorials to serve the professionals in particular and power sector in the whole. I am glad to share with you the excellent support and help extended by SIGRE India in achieving its objective of dissemination of knowledge effectively during current pandemic situation by SIGRE Study Committee D1 through Dr. Jens SIFERT from Germany. You are welcome, Doctor. And we also welcome Shri BP Muni, who is Chairman SIGRE National Study Committee D1, is also a senior, very senior official of BHEL. You are welcome, Muni sir, with whom he is an eminent professional and the subject matter expert and continuously supporting SIGRE India and guiding also the activities relating to National Study Committee on D1 as a you, Mr. Muni. All this great opportunity you are getting from the best professionals in the international and national market, and in this time, whatever knowledge we learn, this is how we grow. With this, I once again welcome you all and request participant to join SIGRE as its member and connect with the global power system community. Thank you very much. Thank you, and you are all welcome. Over to you, Mr. Mani, to address the participant. Thank you, sir. Thank you. Shikha.
Thank you, sir. Now I request Mr. BP Muniji to kindly address the participants. Sir, please.
Good afternoon, sir. Muni, sir.
Okay, sorry, my mic was off. Respected Dr. Bhatnagar, SIGRE India Chairman, Dr. James and Dr. Constantine and participants, I welcome you all to this online tutorial on methods for dielectric characterization of polymeric insulation, insulating materials. And now we have invited Dr. James to deliver this address. And with Dr. James has a wide experience in this polymeric insulation area. And from 1999 until 2018, he was Chief Technical Officer of Labs Insulation Europe, Station Germany. Then he is right now Technical Director at Reinhausen Power Composites of Germany. And he has more than 20 years experience in case of SCD1 activities and B2 activities also. And he is also member of IEC Technical Committees 36 and Technical Committee 15. And he has vast experience. I request participants to listen carefully to him and try to take knowledge from him. And I would like to say that SC1 committee is basically dealing with materials and emerging test techniques. And we invite all the participants to give a name to become member of the national committee so that we can have a future any conference or workshop for this information. And with these few words, without taking much time, I request Dr. James to deliver the tutorial. Thank you. Over to organizers.
Yeah, good afternoon, ladies and gentlemen. Greetings of the day to India. I try to share my screen now. and hopefully this works. Make it bigger. So can you see the screen?
Yeah, we can see the screen now.
Okay.
Yes, we can.
Okay, perfect. Then we start now. The tutorial will be around 19 minutes, including questions, and I would propose that we have the questions at the end. So please note them, and we try to discuss and answer them after the meeting or after the session. Actually, 1 year ago, I was in New Delhi in the symposium in 2019 and made the tutorial about fingerprinting of polymeric materials. Maybe some of you remember me. It was a very nice event. It was, I think, more than 250 attendances. And yeah, this time, different times. So we have to work with web meetings. And so we have practices during the last 9 months pretty often. But hopefully I can encourage you and bring you in the same situation as in a live meeting. About my person, I'm from Germany. I'm working with Reinhausen Power Composites in Germany. Before I was almost 20 years the CTO of lab insulators in Europe, working with composite insulators mainly. From 2018, I'm working with Reinhausen Power Composites as a technical director. Presently, I'm chairman of IEC TC36 high voltage insulators until 2024, then this mandate is finishing. I am or was the convener of D159, so the presentation of the work of this group today. I'm the secretary of D158. I was the former convener of D127, and yeah, I'm working in many working groups as a supporter and to make contributions. So in standardization work in SIGRE and mainly in D1 and B2 and in IEC TC36 mainly, I'm engaged for more than 25 years now. For today's tutorial, what are the takeaways, the key takeaways for you, for the participants? One thing is we will learn about dielectric diagnostic methods. So general insight on these methods, what is time domain analysis, what is frequency domain analysis, understanding the physical background and polarization mechanism, because they are important to understand what's really happening in the materials. Application of these methods to composite insulating materials, because you know polymeric materials are quite complex materials. There are some decades in the market, but still there's some unknown features and some phenomena going on that affect the aging of these materials that we want better understand. Then the actual work of the group, the development of a recommended test technique, the round-robin testing, which is important in these groups in D1. They do a lot of round-robin tests and collect the experience, collect the results, and find a way how to standardize this. The importance of standardization of method and equipment, because you know what's today in SIGRE will be in some years in IEC. And as my professor was saying, SIGRE is a kind of friendship. IEC is business. That means the methods that we apply in business, in the IEC, must be sound and reliable. And because they are fundamentals for contracts and for large order deliveries. Lessons learned. So normally when we close a working group, we have a lessons learned session. And to learn what can be better in the future, what was good, what bad. So we report this to our study committee and yeah, learn from it. Oh, and one thing we can give, what we're doing here was not only for fun, but we want to give you an outlook to applications for insulation systems and high voltage equipment. Means that what was studied here on the material side can also be applied to insulation systems like cable terminations, cable accessories, transformers, and even more complex equipment. So that will be I think the subject of today. This is a product we produced. Normally, these working groups are working for target times of 4 years. This was given by the technical committee of SIGRE, and in most cases it's not possible to finish a work, experimental work, within 4 years. So my group took 6 years, which is a little bit over exceeding the limit. But if you look to the large numbers of members, I can tell you it was the most complex working group I ever handled in my time. It was a mixture of, let's say, scientists, people from industry, people from universities, from material testing, and some other stakeholders. Even young researchers were participating here, students, because the work was very interesting. So you have a wide diversification of persons involved, but we have listed here some other members, the contributing members. These were the members who really did the work, who did the experiments or contributed to the series. A lot of the work that was performed here was a theoretical work. So bringing the complex physical processes into engineering comprehensive formulas. When you start the work, normally you cannot start it from your ideas or from your motivation. So you need to have a kind of order, and this kind of order is named terms of reference in SIGRE. Here you can see our terms of reference. So our title of the group was defined, and you define a scope, what you really want to achieve. And within the scope, you have a definition, what you can or what you shall deliver. And so it's more or less left and right of the area you can work in. And here was given final report by 2017, which was not, I think at that time, not realistic. Then it is approved by the chairman of the technical committee, it was Mark Waldron at that time in 2014, and then you start the work. The idea of this D159 terms of reference was to make an initial characterization of polymeric materials. So define a method or methods that you can say this is a healthy material, this is a new material, and this is what you get at the beginning. You can compare this a little bit with other diagnostics. For example, if you take a blood sample, then you have a reference in the background. You see, okay, a healthy person has these values left and right, up and down. And with time, some illnesses going on or something is changing. Then you take other samples, you verify the results and compare them to the initial results, and you can make your conclusions out of it. So develop countermeasures or taking out the stress or whatsoever. And so the group scope was actually only to define the conditions for the initial new material. We went a little bit further. I will show you in the results. So fortunately, we also had some possibility to study some kinds of aging mechanisms, mostly related to moisture, because you know the greatest enemy of composite materials is moisture. Moisture is penetrating into interfaces, is diffusing into materials, and therefore it may affect unwanted processes. So that was the actual idea. So the next steps could be following working groups that looks at the aging processes and understanding in conjunction with complete insulation systems. So for example, make a cable insulation analysis, defines the characteristic at the beginning, and then take samples with the aging time, and maybe you can find out when is the end of life of your cable, when you have to exchange it. And as you know, we want to have our equipment as long as possible in the market. That means the sharper we can determine end of life, the better is the economy behind it. So in the table of contents, what we are going through in the next minutes or next hour is that we have a review of the abstract. We will look into the theory of polarization mechanism. We have I will shortly present the literature review. Everything that you can read is or what you can analyze in detail is listed in this technical brochure. And the technical brochure is quite complex. It has more than 100 pages. And for members, it will be available for free on eSigre. So you can download it without any payments. It will be available. So we have submitted the technical brochure. We have submitted the Electra paper. The tutorial today is a part of it, of the whole package we have to deliver. We expect publication by the beginning of next year. In the technical brochure, you will find a very broad literature review, because the technical matter dielectric diagnostic is not really new. So we have seen that it's applied for more than 40 years in different technologies and different applications on different materials. So we have reviewed the test methods, and we have selected the best one for our test specification, which we under 6 defined for the round robin test. I will also give you a look into the test results and to see what conclusions we can derive from it. And I will finish with recommendations, same recommendations we have given to our study committee. Once per year, we conveners have to report to the study committee, E1, about the progress. So a little bit like project management. So you have to give the status, you have to say what kind of resources and meetings you need. The only thing is that you have not a real financial support. Yeah? So you have to do this with your own motivation and with volunteer work. That's also a great part of SIGRE, that we put our resources together and try to understand complex situations and to solve it together. That's the ghost of SIGRE. Yeah? So it's not a commercial organization. We try to fix problems. We try to solve them. I think that I already told you we have started this work in 2014 and we have finished right now. I think for sake of this terrible COVID situation, we got the report written. It's also sometimes a mission to get this completed when you work with such a large group. So we have many reviewers, we have many guests that check the report and check the matter on soundness. So it was quite tricky, and hopefully we manage this. So we will talk about composite insulating materials. Composite insulating materials are today considered as emerging technology. If you look into cable insulation, in composite insulators, dry type transformers, all these oil-free, SF6-free apparatus work with these composite insulating materials. And the uncertainties are here. That's one of the main troubleshooters in composite insulating materials, which are interfaces. Interfaces you can have as a macroscopic interface between silicone and epoxy, or between metal and the composite material, or you can also have microscopic interfaces. Microscopic interfaces are interfaces between a metric system and a filler, for example, a quartz powder or alumina or glass fibers. And interfaces may be very complex. So these are the standard ones that are taken for the theoretical investigations. So typically you can have a normal interface or a normal directed interface. You can have a tangentially directed interface, or you can have a mixture of both. And when you think about glass fiber reinforced polymers or mineral filled polymers, then you have a very diverse and wide and complex arrangement of interfaces. But to understand which kind of interface is dominating, these three models, normal, tangential, and normal tangential, are defined. Going back to the actual polarization effects in solid dielectrics, it's taken from a book, from lectures of professors, of course. It's not a new invention. What we have to look at today is time starting from some microseconds to hours, months, and years. And the polarization mechanisms behind are mainly driven by space charge polarization, so ionic polarization, hopping polarization, and orientational polarization. So dipoles, yeah? That's the range we are looking into the physics when we talk about composite insulating materials. Electronic and atomic are too fast. They are not interesting for us. They are more interesting for electronic materials. For example, in this range, space, charge, and ionic polarization, we mainly talk about the Maxwell-Wagner effect. Maxwell-Wagner effect is a dominating effect in composite insulating materials since it affects acts at interfaces. So you charge or discharge space charges or ionic particles in and along interfaces. So the Maxwell-Wagner and so-called accumulator effects, these are the main effects we have to look into. So, and what we also can see here, we have to look at long times. Long times means low frequencies. So after reviewing the available procedures and methods, so we found very nice methods coming mostly from universities and from scientists, which are called time domain spectroscopy, TDS. It's a very interesting way to analyze materials. It's like it's given here on the left side a very simple scheme. So you have a stimulation. It's normally a step voltage, and the step voltage is has a response which is called current response, and this current response is given by the quality and nature of the dielectric. And so normally what you do, here's the theory behind it. So you have a polarization contribution, you have a conductive contribution, here's the polarization, here's the conduction. So you normally use like a kind of Laplace or Fourier transformation, DFT, to transfer this or to transfer the transform the response function into a spectrum, into a frequency spectrum, and from this frequency spectrum you can see what kind of effect is in the material. It's most probably the most effective method because it's not time consuming, it's easy to apply. What are the difficulties? Difficulties are measuring the very low currents. So the currents are in the range from starting in the range of nanoamperes via picoamperes and femtoamperes. So main challenge here is to have a noise-free, distortion-free measurement of such low currents. And this is possible in shielded arrangements, but we found it's not so good in industrial applications because the required conditions are hardly to realize. Interesting methods. It's, you find a lot of papers given in the literature review, and it's also used in transformer diagnostic, by the way. It's very close to applications, but for materials, we selected this method here. It's a frequency domain spectroscopy, also called FDS. In FDS, you take a voltage phasor as a stimulation signal, and you get a current phasor as a measuring signal, as a response. And, this is a very simple arrangement. You vary normally the frequency, so you're starting at very low frequencies in the range of some millihertz, and then sweeping into the kilohertz and megahertz range, and you get this current response function, which also is divided into a capacitive part. Let's see, a response given by the permittivity, and also a contribution given by the conductivity. So both methods consider conduction effects and polarization effects. And from this calculation here, you can derive the complex permittivity, which is epsilon 0 multiplied by epsilon R1 and epsilon R2, the complex function. And in the complex function, you can distinguish between polarization and the conduction part. The conduction part is given here. Both are depending on frequency. And so derives the tangent delta. Tangent delta is also known as loss factor. And the loss factor can also be splitted off in the polarization part. So it's the dipoles where you lose energy by friction, and you have also a loss by conductive mechanism. So it's a very clear and comprehensive theory behind, and it's just about the evaluation of the complex permittivity. So what can we do with the results? So this is mainly from a very good book made by Yoncha in the UK, from Chelsea study group, a dielectric study group that worked in the 1970s, 1980s, which derived a lot of physical mechanisms that can happen in moisture affected or aging affected polymers and composite materials. And this is a summary of what is written in this book. So it's a list of typical dielectric phenomena in solid dielectrics. So we start with the simple ones. So you know the debi-relaxation, which takes place in the high frequency range. Here's a kind of non-debi. It's a mixture of many mechanisms taking part in the multi-100 megahertz area. As I mentioned before, we have to, resonances are also in the optical range. They are not important for us. So we have to look at 4, 5, 6, 7. 4 is interfacial polarization taking place in the low frequency range. This is the Maxwell-Wagner effect. So this half circle here or semicircle in the low frequency range is the Maxwell-Wagner effect. 5 is an ionic conduction, which is theoretically a straight line in this diagram. This is also called Cole-Cole plot. Yeah. This is epsilon 2 versus epsilon 1. It's a standardized method to recognize what kind of mechanism you have in your solid dielectrics. So the ionic conduction is moving from here, it's infinite. So you have ions flow everywhere, and it goes down with the frequency. So it's a straight line. 7 is a low frequency dispersion. And this one is the one that we applied for our analysis. It's actually a mixture between the Maxwell-Wagner effect and the ionic conduction. And this is where the theory and the engineering equations come together. So it's very difficult to make just one model for a complex material like a polymeric material. So this is why in engineering, we concentrated on this line here. So this is what we see in the later results from the lowest technical detection limit, which is around 0.0001 hertz, 10 minus 5 hertz, to the technical frequency 50 hertz, until you get a gain again in the permittivity, especially in the loss function. So we see in the results mainly this curve here, this U-shaped curve. I start with an example. What you can see of a material that is aged or stressed. Here, on the very left bottom, you see a new material. You see a cold plot of material. It's difficult to see. It's a very small dielectric response. And now we apply, this is a kind of quartz powder filled epoxy applied in auto insulation or in transformers. Now we overstress the material. So we apply lightning impulse voltages, 500 impulses, 2000, 5000. Here sometimes we see breakdown, yeah, at this point. But some materials also resisted more than 10,000 impulse voltages. And so these materials here may look from outside, look pretty fine, but inside they're already damaged. They're damaged by treeing, they're damaged by voids, partial discharges, carbonized areas. So should we work further with these materials? Also, they withstood so many lightning impulse voltages. For me, the answer is very clear. The answer is no, because these outer circles here, these semicircles, are in reference much far away or much farther away than samples where we already had breakdowns. So you can see this is maybe a limit fingerprint where this material is end of life. It's just an academic example. It's not on real, not on real installation, just on small sample installation. Here's a second example. It's has investigated the influence of moisture. New sample, if the material comes out of the production machine or out of the laboratory equipment, you have a very low dielectric response. You see the circle, so the Maxwell-Wagner effect. And this sample was water immersed by days in 50-degree hot water. So after 6 days, 8 days, 10 days, 13, 15, 17, 20 days, you see that this Maxwell-Wagner effect is increasing. That means in the interfaces or between the interfaces of the material, you get already a kind of a space charge or space carrier effect accumulation. So the material is aging. Also from outside, it looks it's not changed. So you see with this method, you can clearly see a change in material. And by the way, these methods are non-destructive. It was also one aim, or was also given in the scope, that we should develop non-destructive methods, because we want to apply it in systems during different aging stages. So afterwards, the equipment shall be energized again and stay healthy. This is a collection from literature. So we reviewed more than 100 papers. It was the first part of the working group. And if you're interested in some details, or if you're searching for a specific kind of application, this table is showing the method, showing the reference, test parameters, what method was applied in which range, under which conditions, what kind of material, the kind of sample, and sometimes you see also application. Here's high voltage auto applications, transformers, switchgear, rotating machines. So it's a really a good list where you can work with, or when you want to select a specific example, what is already existing, then work with this literature review. And we have in the brochure, you have two references. One is the normal one, starting from 1 to the end, and there's the E1 to E33 or 38. And the E references are for examples. So don't be confused if you read the technical brochure. This was done by intention to distinguish examples from the main literature. Okay, so we selected for the frequency domain spectroscopy. I come to this later why. And also we selected the contact-free method. So you know that in dielectric testing or determining the permittivity and tangent delta, you have two methods. Left one is given in the standard. In today's dielectric test standard, when you want to measure tangent delta and permittivity, you have to apply the method on the left side, which is known as contact method. Contact method, it's easy. You take two plates, put the sample in between, measure the thickness of the sample, and you normally work with the gartering arrangement on the ground electrode. So you have a measuring electrode in the middle, because you don't want to measure the surface, or you don't want to have an influence of the surface currents. You just want to have the bulk currents through the material. And your analyzing equipment is connected to the top and bottom electrode. Both methods determine the impedance. Z, it's a complex impedance. It's a complex phasor divided by the complex current phasor. Then from here, you calculate the complex capacity. From the complex capacity, you can derive permittivity and the tangent delta. So that's easy theory. What are the problems? It's even more simpler on the left side, because here you're just working with geometrical factors, so you don't have other disturbing factors. But if you look to practical measurements and practical samples, maybe you're working with silicon rubbers, then it's easy because the electrodes are contacted smoothly to your sample. But if you work with duromer material, or with materials that are not a smooth surface, then your contact area that you use for the calculations is not the geometrical contact area. It's just the contact area that you get from the sample quality. And this may lead to errors and uncertainties in the results. So we explored both methods, but we selected the right one. The right one is the contact-free method. And when you look to the samples or to the arrangement, there is no guard ring. And you see a gap between the top electrode and the specimen, which is good, but is also part of a problem, because you have to calculate the air capacity and you have to calculate the sample capacity. At the end, you want to have the sample capacity, and from the sample capacity, you can derive tangent delta. Also in this equation here, you see different kind of disturbing or potential disturbing factors. One is K, that's the correction factor for the electrical field. You see dr, these are geometrical disturbances, or it's a correction factor that you have to calculate, and you see the test voltage. And all these 3 or 4 can be disturbing factors for the quality of the results. Yeah, the contact-free method is also called air reference method. Yeah, so you take a reference without a specimen, and then in the same arrangement you take a specimen with you take the same arrangement with a specimen, and from this, from the theory behind, you calculate the complex capacitance. What was done here? We worked normally with fixing the electrode in a distance of 2.5 millimeter. And so here is one challenge, of course, is the adjustment of the distance. We did this by precise distance measurements or length measurements. You have to determine the thickness of a specimen. That's normally when you get material samples out of a laboratory, the quality is not better than 2 plus minus 0.2 millimeter. So you have a certain kind of scatter because of the production and method how you produce the samples. And finally, you need to measure the capacitance and measure the complex capacitance C2 of the test cell, but with specimen inserted. And from these values, you can get then the tangent delta and the epsilon R value. So the epsilon value is the real part of the permittivity. Then you have to calculate the epsilon 2, which is the imaginary part. And from both parts, you have a correction here on the real part. And then you can have you have to do this because of the air reference. And here you calculate the tangent delta, the loss factor, as a epsilon 2 divided by epsilon 1 corrected. This is how our selected method was defined. So this is a technical drawings, more or less, how we defined the test procedure for the round robin test. So we also defined how to connect this with the BNC bushing with we put everything in the shielding box, made a standardized connection to the voltage application, grounding, defining everything, which was in the lessons learned very good, because if you start to make own equipment or to start to work with undefined equipment, that's a big source of error. That we already learned from former working groups, that we clearly have to define test equipment and arrangement. So everybody got such a box. They were done by one manufacturer or by one university, Chalmers University. They built this box, and everybody got this box for the round robin test. And we also standardized on gauges. So we took gauges from the same supplier. Gauges are used to apply the distance between the electrode and the specimen, which is the major driver of measuring mistakes. And we described also how the shield box must be connected. Also here, you can do a lot of things wrong. Although the whole equipment in the bottom part looks very simple. Yeah, it's not a sophisticated setup, experimental setup. It's just a shield box with the electrode arrangement and a commercial instrument. Here you can use different ones. We used most of the applications. We use this frequency domain analyzer. So they are applicable or available on the market. So you can use a commercial one, you have to define the measuring range and the measuring voltage. And all these devices are calibrated today and have the same, more or less same procedure in the background. You can connect them to computer systems and get analysis results very quickly. And also most of the devices assists you in the evaluation. Contact-free method, this is how it looks like. So this is a test arrangement. And what you see in the upper right picture is the setup to the gauges. So the 3 is a gauge that is used here for control of the distance between the electrodes, which is a challenge because also what we see later in the sensitivity analysis of the failure of the error mode analysis is that the spatial geometrical conditions are essential for the quality of the results. It means if you have a not parallel arrangement of the plates, plan parallel arrangement, this may affect the results. The distance has a tremendous impact on error. Also, area measurement and thickness measurement of the sample itself are contributors to errors. So you use 3 gauges here in the upper left picture, same from this, all from the same batch, from the same package, and so you adjust the arrangement on 3 different sides. Sensitivity analysis, and this was really thanks to Professor Derek Oliver from Winnipeg University in Canada, who is one of the best experts, in my opinion, in this field. He did a very theoretical, but also assisted and supported by experimental work in the background, and he found that the spatial geometry, which is given with the delta dr, has also an impact on the accuracy of the correction factor. So if you do it not in the right way from the beginning, the arrangement is not fixed as it should be, then also other factors are negatively affected. It means it's like a chain reaction. Yeah. So if you do it in the first step, then your other steps are also not very good. And so you have the main contributors to errors in the measurement are the geometry factors, test voltage quality. And this is not the voltage itself. It's the way how noise is affecting your generator. So we are working in a range starting at low frequencies with low currents and moving into higher frequencies with higher currents. And in between, the noise is given by 50 Hertz disturbances, by other disturbances like welding process or the quality of the net. Yeah. So it's also not to underestimate this factor quality or voltage quality. Quality of air is a minor influence. It's mainly the moisture, but accuracy of the correction factor of the arrangement is a contributor. So these are both the failure or sensitivity analysis for the quality of permittivity and the analysis for tangents delta. You see the main contributor are here. So if you want to measure epsilon in a range of 2 to 5, where most of our applications are, or tangents delta in the range from 10-3 to 10-1, so you can have quite high disturbances here. And this is also lessons learned for future groups. You can, with this method, you can see qualitative effects. You cannot, or you should not use them for quantitative analysis. So you can see a trend, you can see a tendency, you can derive from this tendency certain conclusions, but you should not work with absolute values. That was the lessons learned from analysts. It was a warning here, and it came out in the results exactly in the same way. Voltage of the influence of voltage is not so big, and here's in the air gap is also not significant. Disturbances here. So all factors that influence the spatial geometry we have to take care of. It means measurement of dimensions, measurement of thickness, measurement of the air, control of plant parallelism, and quality of samples, of course. Here, it's one sample. It's an easy one. It's a silicon sample, HDV rubber sample that was used here for illustration, how you measure it between polycarbonate sheets. Sandwich is measured, and you can see on the accuracy of the device how good you can measure. What you do in the round-robin test, you don't rely on one sample, and you should not rely on one sample. One sample is no sample. In this sensitivity analysis, Professor Oliver also investigated the influence of the numbers of samples. You can bring for each element down, significantly down, by measuring 5, 10, or 20 samples. Okay, if we measure 100 samples, we have a low error, but maybe not economical anymore. So we have to find a good compromise. For this round-robin test, a sample number of 5 was good. I think for later practical applications, you will not measure 5 cable slides or 5 cable samples because you cannot afford to do it, or you have not the time or not the resources. So this is one thing we have to look at. We have also recorded in the lessons learned. Yeah, now the theoretical part is more or less finished. So now it comes to the test procedure. In the work in the fingerprinting and in the tracking and erosion experiments we did in D127, it was found that we should have a really good test specification. With the test specification and the quality of the test specification, people start to work. For example, in this case of this working group, we had 7 participants, and they're sitting in different continents. So one lab is in Canada, 2 were in Germany, 1 in China, 1 in Sweden, 1 in Argentina. So you're working not in one group. You're working under different conditions. The temperature in Canada may differ from the one in China, or humidity conditions may differ. And this is intended. So exactly what we want to do is to apply this method, or to explore this method under different conditions, done by different workers, done by different, under different control conditions. This is why we do this, because we have to develop a method that is at the end representative, repeatable, and cost affordable. So we have to apply this method in an industrial way at any site we can imagine in the world where we want to get this value. This is one of the rules, or the 4 rules of IEC. If they are not fulfilled, such a method will not enter the world of IEC standards. So with the specification, so we defined fixing gap to 2.5 millimeter, using standard gauge blocks as reference, precisely determining the thickness of the samples, cleaning, that's also important. If you ship the samples to Argentina or ship them to Canada, they're in different conditions than you have submitted them from your production. So cleaning is very important, cleaning of samples and electrodes, taking care that electrodes are not corroded by means of specifying non-corrosive electrodes. The drying conditions, because polymer samples, of course, absorb water by diffusion, so you cannot control it. On the way to Argentina, on the way to China, they are collecting water, they're absorbing water. So we need to bring them back into initial conditions, because we want to characterize initial conditions. So we have to define drying procedures. Temperature, if you look into Arrhenius equations, and Arrhenius is coming along with dielectric phenomena, because you have energized states in dielectrics, all depending on temperature. The temperature has a very large influence on the dielectric phenomena. So we have to control the temperature, perform the measurements at various frequencies to obtain the complex capacitance. Do all the things that are written here. And finally, we need also to standardize on data processing, because the first results that you get from Argentina looks completely different and in a completely different format than the results you get from Canada. So we have made standardized Excel tables where you can fill in your data at which frequencies and which number formats. And repetition, of course, is repeatability, and is an important thing. Repetition means repeating it in the same laboratory. So you should obtain the same result in a repetitive measurements. And repeatable means if you measure it in Canada, should be same result as in Argentina. Some key hints here. Do not move or adjust electrode system after the reference method. It's for, I think for expert it's clear, but lessons learned was different. Fix the gap distance to 2.5 millimeter. Use a shielding box to avoid external interferences. Connect via BNC. Do not use oversized specimen. Sometimes you say, okay, my measuring area is 100 millimeter diameter. Take a big plate and put it under the electrode. Don't do it because it affects the factor K because of the stray field. Determine precisely the average thickness of the specimen as well as the air gap. As I mentioned before, these are the main error modes or error contributors. Clean the specimen. Always check original capacitance data. So there's the self-verification of the equipment, the self-testing you have to do. Sometimes these electronic devices are not in a zero status. Secure proper grounding of the measurement equipment. Avoid loose contacts because these are also potential failures. You can maintain stable environmental conditions regarding temperature and mainly humidity during test. Store the samples afterwards in a dry area, maybe in an oven, if you want to repeat the measurements, or if it's a plan of the round robin just to repeat it after some days. Actually, this was our main scope to work with this kind of characterization of new materials. So, but then we decided by the way, we had 14 working group meetings, 2 per year, and the last one were virtual, but you can imagine that if a large group of 30 people or even more sits together, there are a lot of ideas coming up, and some of these ideas are good, sometimes we followed them up, sometimes we forgot about, but here was a good one. It's a water immersion because, as I mentioned before, the interfaces, the microscopic interfaces in composite insulating materials are mainly affected by moisture. So we can trigger with moisture potential aging mechanisms. So we can stress the material in an easy way. And most probably, this is also the dominating aging effects that we see on the real application in the field. So we defined a procedure. What is water immersion? So we dried the samples first at 100 degrees for 6 hours. With contact-free measurements, we want to measure. We use distilled or deionized water and place the test object in water for 50 days at room temperature. You can even promote the aging if you increase the temperature. So there's a rule: if you increase the temperature by 10 Kelvin, according to Arrhenius, you get double the process behind. So if you have a diffusion effect or diffusion mechanism, that is depending on this equation, then you can, by increase of 10 Kelvin, you double the speed of diffusion of water into the material. So you can imagine, and there's also some limit. You can do this, for example, with eggs. Yeah? If you increase the temperature, you can speed up the breeding. But if the temperature is too high, then your egg is boiled. So you don't see the original effect anymore. You get a change in effect. And this is why we limited it to 50 degrees, because we know that most polymeric materials are changing not the aging mechanisms in this range. Above 50 degrees, there may be a change in the aging mechanisms that we do not simulate in the right ways. Complete the contact-free measurement according to the described procedure at room temperature. Dry again for 100 degrees for 96 hours, and you can check whether this is a reversible effect or whether it is irreversible. So this was actually not the plan, but yeah, hopefully or fortunately we did this, and also it has a real good insight for us what's going on with these materials. Yeah, now most of the people are not attending today, but these were the real workers. Yeah? So if you perform a round-robin test, you have to have somebody who makes a test, to spend time, to spend the money. In most cases, these were universities, as you can see, University of Manitoba, in Winnipeg, Canada, Chalmers University in Sweden. It was a Professor Kubanski, maybe you know him from, he's now retired, but he's a great expert in this field of dielectric phenomena. Professor Kornhuber, and together with Professor Bersch from Zittau, they are also deep in the field of dielectric materials and testing of materials. German Salvo from Argentina, from Edenor, who his company is working in diagnosis of equipment mainly. Also in other materials, you see the University of Munich Technical University of Munich, Professor Kindesberger and his team. He's also retired now. At that time, he was also chairman of SCD1 and also main initiator of this work. What you also see here, not everybody did test with the same materials, but most did test with the HTV rubber. It's a commercial grade silicon rubber that is used mainly in composite insulators and cable terminations. Liquid silicon rubber, same application range, going also deep into the cable systems. EPDM from cables and also from former insulators that used this as housing materials. Epoxy resins, a wide group of materials that is applied in medium and high voltage equipment, maybe in internal insulation. And most of these epoxy resins are filled with a mineral filler, with quartz powder, in order to set up the desired conditions. So this was the round-robin test. So at the end, we performed 3 of them. One had the explorative character, so it's just sending out some samples and see what's coming back. For a round-robin test, you need a very strong coordinator. And in this case, this was Professor Kornhuber, Stefan Kornhuber from Germany, who really got all the laboratories controlled and also not controlled, but also guided and encouraged what to do and how to send the information back. And he was really quick on evaluation. That's also from the lessons learned. If you do this, you have to be response time. So the feedback circle, the feedback loop must be very quick. Otherwise, you're losing time and sometimes you're losing your mind and the results are not of good quality. So it's thanks to Stefan. He really managed this in a perfect and professional way. He collected all the data. Also, with this data, we decided what we do next, which kind of round-robin test. So from the second test on, we were in the real round-robin test mode. So we did one to characterize initial conditions, and the third one, the second one for this purpose, and the third one just to validate the results and also to study aging, which was not on the plan from the beginning. Here you see a typical result of this round-robin test. So it's a classical diagram. You see epsilon1, which is the real part of the real corrected part of permittivity, and given versus frequency. Frequency starts at 10⁻⁴. That's the lowest technical limit the device can do. And you can imagine that such a measurement takes some time in order to sweep all frequencies, because you need to stay at one frequency for a while. Yeah? So it's time consuming. Although it looks like a sweep, such a testing will take you some hours. And what you can also see here, here's different laboratories. So we see that all show more or less the same tendency, but they have different starting points, initial points, and they have different points in the higher frequency range. So it means here the error mode or the error mechanism is impacting the quality of the the test results. Some come very close together. Some here in the higher frequency range, they are good. For example, when we do normal measurements on a technical frequency of 50 Hertz or 60 Hertz, we are here in this mid-range. Here we see relative low scatter. But we should not forget, we have applied the air reference method. So with a method at 50 Hertz, standard method, you will get more accurate results. Here's the same for the permittivity 2, with the imaginary part. Also here, same tendency, but in absolute values, a wide band of scatter. This is interesting. This is what we used for the evaluation. This is cold plot. I bring you back to where we are. So look to this diagram. So we're coming from bottom right with the frequency. So the lowest frequency is on the bottom right. The highest is on the left side. Top right is the lowest frequency. Bottom left is the highest frequency. So the parameter frequency goes along from right top to left bottom. And keep in mind how the curve looks like. I go back to another slide now. So what you see in this curve is coming from here, from the lowest technical limit down to 50 Hertz or even a little bit more. So we go into kilohertz or megahertz area, but we are somewhere here in this falling branch of the so-called low frequency dispersion curve. I go back to the other one. So just to give you orientation where we are. So it fits with the theory, and we are looking to the right signal, so to the right range. Because we are searching for interfaces, we are searching for ions, for molecules that are moving, for slow moving effects. Here, what you can learn from here, so the scatter seems not to be so high anymore, but you can see a clear tendency. So all test labs for this material show more or less the same dielectric fingerprint. Here we investigated an HTV material. We have to say this material is filled in comparison to the liquid silicon rubber. Liquid silicon rubber has no alumina hydroxide filler. So it's a pure material, more or less pure material with low amount of interfaces, actually theoretically with no internal interfaces, but also they use some kind of silica to get a mechanical property. So also these materials have some kind of interfaces, but a low amount. This material here has, by material formulation, a higher amount of internal interfaces, just given by the filler loading, which may be between 50 and 60%. 50% of the elastomer is mineral filler. You can imagine how many interfaces you have between the fillers and the polymer when you think about that these particles are in the range of 10 to 20 micrometers. So these are areas of, I think, some soccer fields that you get in a small sample. Here, very promising at 50 Hertz, very small scatter, also with the air reference method. And in the low frequency range, you see a little bit higher scatter. But tendency is very clear here, with lower scatter than with the LSR. Why? We think, or we concluded that the interfaces give a clear signal, give a clear process behind the response, and that when this happens, then you really measure something that is really going on. So it's not determined by scatter, it's more determined by a real physical process. Same here. It's the loss part, the imaginary part, the falling tendency. It fits perfectly with the theory. Also, what's there right here is the temperature. You see different temperatures, for example, and so you see a clear tendency in increasing the loss or the imaginary part if you're increasing the temperature. That was not a surprise, but it's confirmed here because you enable more energy levels in the material, energetic levels, that the process is more likely to happen. Arrhenius theory, it fully fits here. And for example, this material we have also immersed in water. And now we come closer to the semicircles. Yeah? So this is Maxwell-Wagner, what's going on here. What we see is the left half of the semicircle. So because on the other hand, it would go down again. Yeah? So maybe here's the top or the top point of the circle, and it will increase and decrease in this direction again. So this is a cutout of the Maxwell-Wagner circle, which is perfectly given here. And this was done here after different stages of water immersion. So start, after immersion, and after drying. And the tendency was clearly with the frequency. So you moving down into the lower losses and lower permittivities. Also, absolute values, they cannot be correct here. As you can see, it's not the absolute values that you get from the measurement of a standardized method. This is a signal for EPDM. And EPDM, also sharp dielectric response. You have to understand that EPDM material is formulated in a very similar way than HTV silicon. It contains normally also alumina hydroxide filler. Alumina hydroxide is a polar filler. It means by its nature, it has a kind of polarization. And of course, you have the contribution to the interfaces. And of course, alumina hydroxide is not only alumina hydroxide, it contains also a lot of water by nature, not only from water immersion or water penetration from outside, but if you manufacture this material, you have a certain amount of bonded water inside. This is by intention because these materials or this filler is used as a fire distinguisher or to setting up the tracking and erosion performance. Tracking and erosion performance is actually like extinguishing fire, extinguishing the arc. So you're using the same philosophy in order to get a good tracking and erosion resistance as making a material inflammable. So that's clear, or at least for us it was clear, that we can have a real interpretation of the results. Also a very strong response here, a clear tendency. There's one, the red curve is a little bit moving out, but I understood later in China they used not a commercial equipment, they used one that they built in the university. It was done by Tsinghua University, Professor Liang Xidong. And later on, what is not in the report, we reviewed the results from China. They did a fourth round-robin test, or let's say a separate test, and with a better definition of the test results, they came to the same curves. So this was not given in this report because the data came at the beginning of September when the report was already finished. But it demonstrated that if we do standardization on equipment, on test configuration, we come all to the same results, more or less. Here also clear signal for Maxwell-Wagner. So you see quarter circle of this phenomenon. Even the results from China, which are out of range, I would say, fit into the curve. Yeah, that's I think the parameter was wrong in China, so they measured a different kind of frequency. Yeah, mineral filled epoxy resin. That what I showed you before. These pictures here. These were same kinds of materials. So you see one material, because of the interfaces, may be susceptible to electrical overstress. And electrical overstress means treeing, means step-by-step carbonization and growth of channels that may lead to failure after time, so aging time. This relates also to the inverse power law. You can load the material and it will not show any kind of aging until you not exceed so-called damage limit. Damage limit theory also applies for materials. If you always stay underneath the damage limit, so the voltage stress or the water stress is lower than the damage limit, you don't see any aging. Same here. That's the curve we have to look at, and the round robin test. You see, this is a good quality material because you have not a very strong response. So the response is relatively flat. And why? This is also the case with the different temperatures. The reason is simple, because this material was a high quality commercial grade using fillers of low alkaline content, low sodium. Sodium is the main contributor to the problem. Potassium is not so critical because it's not fast moving, but the speed of ions is higher with the sodium. So you have to take care that your fillers have low sodium content. And secondly, the fillers must be treated with silane at the surface. Silanization and alkaline content makes a good filler for a good composite material. Same applies for glass fiber reinforced materials. Same applies for all kinds of mineral filled materials. It's also lessons learned here. So the quality of materials can be checked with these methods in a very good way. Imaginary part also in a low range with a relative flat response compared to the others speaks for the same feature, good quality material. You see again the Arrhenius characteristic when the temperature is changed. But you still see a response. You still see the Maxwell-Wagner effect is active. Can also be confirmed here. But with all the data, what you do at the end. So we cannot, for example, you need not an expert to look into such diagrams and to decide whether it's good or bad or what you see from it. In the theory for later applications, we have to bring this to a figure, to a quantitative figure that we can say, okay, here we see a kind of effect, or we see this kind of effect, or we see no effect. And for this reason, we applied the theory of low frequency dispersion. Why again low frequency? Low frequency because we see in the low frequency range the Maxwell-Wagner effect. We see all effects that are interesting and important for composite insulating materials. Why this kind of dispersion? Why we don't use Maxwell-Wagner? Because Maxwell-Wagner is not sufficient to describe what's really going on in the material. So we selected a model from Yoncha. So this number 13. Very good to read if somebody has an interest to go deeper into this very interesting field of physics. Read this book and you will find a lot of URLs inside. We have taken out this equation for evaluation. It's a double mode equation. So it has one part for the low area and another part for the higher frequency area. So at the end, we skipped the higher one. So we just looked into the lower one. Then you only have one N, it's sufficient, because we have almost no effect here in the high area, but 99% here in the low area. And thus we work with N, with just one N. And this N you have to see. N is actually, you have to make a straight line here, extrapolation. Also, your software is doing this, so you have to determine the angle of the slope, and from this angle, from this arcans tangents, you determine by cosinus arcus tangents from these values in the logarithmic description or in the logarithmic figure, you get out n. So it's Stefan has done this by means of self-made computer software in order to have all diagrams under the same observation and under the same evaluation. And in literature, you find the following values. So normally I explain you how you do it. You take this slope. From the slope, you get the angle. From the angle, you get with the cosinus function, you get n. With N, you can look into Yoncha's theory. For example, if you see an N of 0.8, you have a dipolar response. If you see two modes, like here, we have some with two modes, then we have a dipolar response, and the lower one is a conductive response. So it's a mixture of two. So you can filter out different modes of polarization and conduction. This is also lessons learned. So we need a software like an expert system to find out, to detect what's in your materials. That's for the next group, for the continuation of this work. We need an automatic device that gets out of the code plot this kind of N values, or these N values. And this is also given to the big suppliers of equipment like Mega, or I don't know what the names are. So they are the companies that supply such test equipment. They could have a software enhancement to get a module for dielectric diagnostics. This is very important for later studies on real applications, because you cannot hire a scientist any time in a utility when you want to do a cable diagnostic or transformer diagnostic. So you need a kind of equipment that has already implemented this kind of evaluation. N 0.9 to 1 is a classical debye relaxation. Debye is theoretically at 1, and you have a strong ionic conduction if you are lower than 0.1. So it's like maybe you are aware of PD, partial discharge pattern analysis. I can remember it from my university time. It was a mess to read a PD pattern, and somebody said, okay, this is an internal void. No, this is a sharp edge. Or this is contact noise. 3 people, 3 opinions. Today, industry responded on this, and they, in the measurement devices, they give you a kind of expert system to say, if you see this effect or this pattern, it may be a void rather than contact noise. So the help for the user is very important. But we are not here at this target with the available devices at the market. So this is how it works, and this is actually the lessons learned from all of this here, to get this in a device and to standardize the method of evaluating the dielectric response. Coming back to the evaluation of the round-robin test, so for the HDV, it showed more or less a dipolar response. Dipolar LSR, and this is a surprise, showed a more conductive method, which is a surprise at the beginning, but we know there are less interfaces inside, so we don't have the interfacial effects here so dominating. Epoxy resins, they tend more to be dipolar, but they have also contribution by ionic conduction process. So with these figures, you can really assess the material, and you can, let's say, see what's inside your material. Of course, this is for new materials. The whole thing becomes more interesting when you do water immersion or when you do other aging effects. Yeah, this is a test that was done additionally. It was not in the plan to do it, but we said, okay, we want to simulate aging. We want to challenge the material, to stress the material, and we have selected water immersion as an aging mechanism for the group of materials here. So one, you see here we go into the details. Yeah? This epoxy resins, by intention, we used a bad filler. So it's a bisphenol A based epoxy, the state of the art, but we used a filler that is not surface treated. And we used in this case as a reference a good material with a good filler, with epoxy silane treat. And FRP material we used as also to look into it. Specification for water immersion, I repeat it again. We have to define the way we want to store. We want to have the initial conditions. So what do we do before the storing, and how do we handle it during the procedure? Very important. Many scatter came out of not knowing what to do and how to do. So what we see in LSR, it's not surprising. So almost no impact of water detectable. And we have seen this in, so the these are two different labs. The pink one is Canada, the green one is Munich. You see more or less the same, and here you see start after immersion, after drying. So more or less they are in the same range, and water seems not to affect the liquid silicon rubber material so much. This difference between the green and the pink one, it's a difference, or it's still the error that we make with the test method. So we are not fully at the target. So we need to do more. So the group needs to do more. In my opinion, it's easier to work on an application because your capacity and the material input is much higher. So the say the likelihood to have a disturbance on a bigger volume is lower than disturbing a small test sample. It's only my idea, but we can discuss later. Here it's a HTV sample. Keep in mind, minerally filled, alumina hydroxide, 50% by weight. So we see a clear tendency here from the dry response to the water absorbed response, and you can say it's clearly impact of water is detectable. Not a surprise here because besides the polymer matrix, the filler is the same. We see impact of water also here. It's affecting both. It's affecting the loss situation because you dissolve alkaline sodium ions. They are still in minerals. You never get them out completely. And of course, you have water at the interfaces. Water itself has an epsilon R of 81. So any kind of water in this interface will increase both epsilon 1 and epsilon 2. Here's a HTV samples. Sorry, that's it's wrong. It's a wrong headline. I will correct this later on. I will send you also this presentation as a PDF, but I have to make some corrections first. Here, it's forget about HTV samples. It's a epoxy W12, which means no surface treatment. It should actually have a bad quality. But we see also quantitative differences in three labs. Yeah? So, but no clear tendency. It's a surprise. Here, water immersion of in a comparison. So green is the LSR at one. That's the it's wrong. That's the study. What happens if we test only at one laboratory? So how is the difference with different materials at one lab? So that was this question here. So in Manitoba, Canada, they performed the test on LSR, HTV, and EPDM, and you can see they differ. Both materials are not in the same area or on the same line. So they are different in initial conditions, but they show the same tendency. And also here you can detect moisture in each material. Here we have studied different filler surface treatments. And here now I'm on the right way. Strong impact on W12, so no surface treatment. You see big move from initial conditions to water immersed conditions. And you have a minor impact on the surface treated quartz filter in epoxy. So that's very clear, which means we can detect quality of interfaces, of microscopic interfaces. We can detect good, or we can distinguish between good and bad materials. Elastomeric materials. So this is an evaluation with a N mechanism or N procedure. So we see in most cases dipolar response in the dry conditions. And we see a start of ionic conductions. Lowering the N value means we are going into ionic conductions. We are dissolving alkaline ions and we are reducing N. It's also good confirmation here with the LSR stays the same. It's not changing because there are less alkaline ions inside. So the conclusion here is overall the EPDM and LSR show similar behavior during the water immersion. The HDV is much more sensitive to water immersion. Here we studied fiber reinforced and structural materials just by interest. It was not in the scope because actually the material itself was not defined here, but we have taken typical materials that are used in high voltage power apparatus because we want to see, not to study on a material that has no value for the industry. So most of these materials show clear debye response, dipolar response with a 1, close to 1. And also we see the impact of water, FRP, water immersed, is lowering N, which means we are starting a conduction process. So we can see very well here with N evaluation whether we have becoming more conductive inside or whether we're starting more ionic conduction process. Ionic conduction, by the way, in most electrical materials is the starting point for compromising or lowering the electrical strength, because when we talk about the thermal initiated breakdown, which is one of the long-term breakdowns, it's driven by a self-accelerating loop, increasing the temperature because the losses are increasing during stress. Losses are increasing by temperature, and so on. Temperature is increasing, so we have materials running into that, into thermal-electrical breakdown, and this could be a warning sign. Lowering N increases the risk of entering a thermal breakdown. Then afterwards, so that's also a loop you have to do in a round-robin test. Sometimes painful, but it's necessary. So we have to make a review of test specification. This normally you do with the experts who really have gained experience. So Stefan did this in a separate review meeting, not with the whole group, but just with the people who contributed and made the test. So we came to a better test specification here. Then finally, we did another one because at that time, maybe you can remember 5-6 years ago, there was a big rush and hype regarding acid attack to polymeric materials, which occurred under certain conditions. And actually, some people in the working group tried to steer the scope into this direction because it was very present at the time and was feared as a big hazard to the industry. So for this reason, we said, okay, let's try how we can detect such acid attacks. Acid attack is mainly to the surface, by the way. So when we look into acid attack polymers, the depth is some 100 micrometers, and then it stops because it's a self-protecting layer. But okay, let's have a look to the results. Acid aging here. Yes, you see responses, but you see no clear effect of the acid because the acid stays at the surface. And this method, these methods that we have defined are methods for the bulk material, for the volume. So the answer is very easy. We cannot detect surface-related aging effects with such a method. We need to look into bulk materials. Now a little bit over time, but I think I come now to the conclusions and recommendations. The aim of the work was to define methods for dielectric diagnosis and to perform round-robin tests on new initial materials and fresh materials. Also, we were ordered to get good literature review from everything that was published in IEEE, SIGRE, and all other scientific papers. We did this, it's documented, all the documents are available. If somebody wants to have them, the group can supply. We have 3 round-robin tests performed. The message is the test results can be compared in a qualitative way. So we can see tendencies, we can see trends, We even come to the same N values, although our absolute values are not the same. But the fingerprint in the diagram looks always the same, but it lays in different areas, in different quantitative areas. It's like a radar screen. So you see, okay, it's a ship, but you do not see where it is. So it's like the total adjustment is missing, and we are not having an answer to this right now. It's an open question why this happens. The effect of humidity is clearly detectable. The definition of the initial conditions is crucial for comparing the results. It's also clear afterwards. At the beginning, it was not clear. Frequency range, we should work from 0.1 millihertz, not deeper, because otherwise it's time consuming and we do not learn anymore, because the scatter in this high area that we have seen is going up, and it's not necessary. We can see the effect already at 0.1 millihertz. We also have not to go further than 10 kilohertz. So because the effects are disappearing, the ions are very heavy, so they don't move in high electrical fields so much. So they just make a little bit of movement, but not contribute to the response anymore. Effect of acid is not detectable because acid is affecting mainly the surface properties. And then there's a hypothesis. Method is suitable in order to detect volume-related dielectric effects, for example, given by moisture or given by electrical overstress or given by any other chemical-related decomposition of the material that we can detect. But it has to result in a kind of conductive mode, in the conductive decomposition products. The achieved results exceed the expectations by far, since additionally the methods were not solely applied to new materials, but also to artificially aged ones. There was a big honor also given to us, and also thanks by Professor Kindesberger, because he did not expect so good results. Further investigations for the application to complex installations and systems is recommended. So now we can go the step and try to apply these methods to complex systems, because this is really interesting, what's going on here. And for this purpose, we recommended to form a new working group with members, stakeholders for different installation applications, for example, from transformers, cables, bushings, and other kinds of high voltage applications. So I thank you very much. And this is the end of my presentation, but I want to give at the end one slide, maybe also enters a lot of discussions now. I want to conclude and close the presentation with this slide. Thank you very much, and I think I'm happy to hear your comments and discussions.
Thank you, sir, for the detailed presentation of the subject. Now we'll take questions. I request all the participants to ask questions to the gents.
Hi, good morning, gents.
Good morning. Hi, good afternoon.
Yeah, good afternoon here in India. This is Tejpal Singh from G Chennai. So my question is related to the cable insulation test. Like when we perform the cable insulation, is there any correlation between impulse and the DC voltage?
Yeah. Normally, what you perform on cables are different tests. For example, you can do the impulse test, of course, to verify the insulation performance, whether you get the right and specified values. From the DC test itself, it's a factory acceptance test, and also it's a 2 or 3 U0 test that you do with your cable in the factory. And on site, if the cable is underground or undersea, it's more difficult, because the cable is normally long, some 10 kilometers or even 100 kilometers long. Then it's difficult to work with AC voltages. And in this case, most of the generators go down to 0.1 hertz or even lower to not to load the full capacity or to have not the full impedance from the big capacity. So that's, but it's still a setup test. In the literature review, we also dealt with cable testing. There's 2 or 3 papers that where these FDS methods were applied in order to detect quality issues with the cable. So aging of cables, water treeing, electrical treeing. But the tests you were speaking of were more or less factory acceptance tests.
Yes, for example, like when we perform the cable test, like 30 kV or 20 kV, then do we expect the same relations or same result when we perform the impulse test? Or like, for example, if the cable pass 30 kV DC, then can we pass 30 kV impulse, or like the impulse capacity will be lesser than the DC voltage, or it is the same resistant capacity?
From my knowledge, the DC performance is very close to the impulse performance.
Okay. Okay, thanks.
Yeah, if you do everything right with the interfaces, but also in air, DC values are even a little bit better than the impulse lightning.
Okay, you mean in air DC values are better than the impulse?
Yeah, both DC plus and DC negative perform better than the lightning impulse curve in air. But air is a different mechanism. But I expect the same for solid dielectrics. Maybe somebody from the cable world has more insight here, but I'm more from the air and polymer side.
Okay, no, sir. And
but maybe we have somebody in the group who can tell us.
Okay, it will be great. Maybe I'll connect with you offline as well, particularly related to this, because I'm getting the different performance when I'm performing the DC and when I perform the impulse test. Both results are different.
I can maybe my email is also given in the documentation, or I'll write it into the documentation. Then you can contact me on specific parts directly.
Okay, fine. Thanks a lot. We'll connect.
Welcome.
Yeah.
Sali Jens, hier ist der Konstantin. Hallo.
Ach, Konstantin, grüß dich.
Du, super Krawatte. Ja, wunderbar, dich zu sehen. Ja. I have a question. I mean, I like your presentation. You remind me of things I had forgotten decades ago, like coal and whatever else. Now, my question is the outcome of this great and I'm sure tedious work is what? To define, to improve a testing procedure which will enter in a standard someday, and or to get some limit values. In your transparency, you are saying here initial characterization of polymeric materials. Is the idea to get out of this test some limit values, good and bad, for different materials? And this time is not yet so clear to me.
We have discussed in the group the purpose and the further use of the information, and some one idea is it's like taking a blood sample. Yeah, you know that you are healthy, or you know you have 100 people tested, and they show typical results in these different properties. So they are used as a characteristic limiting values. So as long as you stay in these ranges, your body is okay, or your equipment is okay. Yeah? And you have to get this reference values from the new conditions for materials. You know, a typical good material in new condition is in this range. Then this is done here with the work. Yeah? So we know, okay, that's the value where it's good or where it's bad. Now, in the next step, we should go into how far this can change until something happening. Yeah? And so if you go now to a transformer installation or cable installation, and you measure again, and you see difference, significant difference to the initial reference values that are given in a bandwidth, then yeah, something is going wrong, or something may go wrong, and you have to act. You have to replace the equipment or replace the installation or whatsoever. So that's the idea. Yeah? So to say, okay, when we have to do, where are the typical values, where are the reference values, and there's pretty much of work to be done, of course, for different kinds of materials. And for example, when it becomes critical, I compare this a little bit to the gas and oil analysis. So gas and oil for transformers, they did it based on different models and then different patterns and say this is a warning, and if this happens, you should take out your oil or something is going on in your transformer.
Okay, but we have now these values. I mean, maybe I missed it. We have now for these few materials you have tested. Can you tell us these are the reference initial values for good or bad? Is this available?
No, not yet. We have a method how to test, and we have an evaluation how you can get these values. But in the next group, you have to make a survey about all relevant materials. So we did not explore cable materials. Yeah, we did not explore sandwich materials like oil paper or something like this. Yeah? So we need in the next group we need to find to characterize all materials and then find out what are typical values. That's right. But this was not the scope here.
I mean, but this is an exercise for years. I mean, this will take years.
Gas and oil took 4 years until we came to the point where we are.
It would not be. It would not make sense to select, materials which are used. I mean, I have been dealing with, like you, with composite insulators. Let's say, why don't you start? We'll characterize HTV materials, which now 90% of the insulators in the world are using this material. This would be for the industry a good guidance. They know, yes, with this test method, if our material is passes or it meets these reference values initial, then we have a good material.
Yeah, that's exactly the next step. So first of all, we have a method. We need to know what to measure, and now we have to go in the next round and apply this. Yeah? And with application, you get more and more results.
Okay,
and this is, I think, the first step we have done here.
Good luck. Good luck. Excellent work. Good luck, Jens.
Yeah,
thank you.
Thank you, Konstantin. Appreciate it.
The questions. Any other questions for Dr. Jens? Participants may also send their queries to SIGRE India for forwarding the same to Dr. Jens. So with this, we close this question and answer session for this presentation. At the end, we convey our gratitude to the dignitaries for their presence. Dr. Jens SIFERT from Germany for his presentation and support to SIGRE India. Dr. Constantine, former chairman, SIGRE Study Committee B2 on overhead lines. Mr. BP Muniji, national representative in Study Committee D1 and General Manager BHEL for his continuous guidance. And Shri A.K. Bhatnagarji, Director SIGRE India and CBIP. At the end, I convey our gratitude to all the participants for connecting today to this international tutorial. I thank everyone for their participation. Thanks a lot.
Welcome and take care, and see you hopefully next year again physically.
Yes, sir. Yes, sure, sir. Sure.
Thank you.
Bye-bye.
Nice lecture.
Bye-bye. Thank you.
Thank you. Thank you, everyone.
Thank you.
Thank you, sir.